My name is Ning Zhang from Tsinghua University. So today I will talk about the planning of power system under high penetration renewable energy. The first is I would like to give some background on this. The renewable energy in China and around the world has increased a lot in the recent years. For example, this chart shows that this is the renewable energy development. So in orange, it shows the hydro. The hydro is not increased a lot during the last 10 years, but the solar and wind had increased a lot. The wind has a rapid development from the 2010 to 2015, and the PV is developing very fast from 2015 to 2020. So now in China nowadays is the largest country for wind and solar installations. And this is not the end. This is just the beginning of the development of renewable energy. We can see currently now in China, about 1/3 of the electricity is produced by renewable energy. Among them, only 1/3 of the renewable energy is from wind power and solar. But this percentage will be increased to more than 45% until 2030, and this percent will be increased to more than 70 in 2040. So the rapid growth in the renewable energy brings a lot of challenge. We can also see from this figure that we are here now in 2021, and here is the development of wind power and solar, which is both of them are almost about 300 gigawatts. And the target is that wind power and PV will reach about 1,200 gigawatts until 2030. So this is a big challenge for Chinese power system. For example, because renewable energy is intermittent, and also it integrates to the power system via power electronic devices. So this is completely different from conventional generators such as thermal generator or hydro. So it brings a lot of challenges. We sort up all of the challenges and solutions to accommodate high penetration of renewable energy. The challenges can be categorized into stability transient state. For example, we have a low high voltage right through, and also we have a frequency regulation issue, also protection issue, and even lower or zero inertia issue. And also the challenge include operation and also the planning. The challenges can be categorized by the integration of different stage of renewable energy. That means the medium stage, higher stage, and ultra high stage. Currently, the power system around the world and in China are still in this stage, I mean medium penetration. So we are not facing a lot of challenge, but some of challenge appears. Some of the country are in this stage, I mean high stage, that mean about nearly half of the renewable energy is from wind power and solar. And these power systems are facing more challenges. And there's no one power system that enter this phase. That means more than 5% of renewable energy is produced from wind power and solar. We do not think hydro is a variable renewable energy because it is conventional and it is quite similar to thermal energy in terms of its technique, in terms of its technical characteristics, such as it is not variable, it is not power electronic interface. So the renewable energy here will only denote wind power and solar. And also in the right half of the figure, we also categorize all of the technical solutions to integrate high penetration of renewable energy, including storage, including demand response, including multi-energy system, or even including power-to-X carbon capture technology. All these technologies are also categorized into different stages and also in terms of the cost, because different technologies has different cost. And we find out that there's not a one-to-one map of which of the challenges can be tackled by which of the solutions, but the mapping is really, really complex. We can see from this figure that we have a lot of solutions, and each solution do not have a single map to the challenges. For example, the energy storage, it can solve multiple challenges. So how to decide what is the future shape of the power system under high penetration renewable energy is really a complex task. Today, I will share some research outcomes from our group about how to plan the future power system under renewable energy integration. So first, I will introduce power system operation simulation technique. This technique means that in traditional power system, in the power system planning, we only need to consider the typical power system operation mode. That means power system under summer days or under winter days. When we plan in the power system, we only need to consider the operations of our system under extreme days. But however, for renewable energy, because it is variable, so it varies a lot. And so under this situation, we need to have a day-by-day simulation of power system in the future, and then day-by-day simulation in the future, and then the power system planning can be assessed in detail in the future. So the detailed framework is that the power system simulation framework, the year-round simulation, I mean, have three stages. First is renewable energy operation simulation. That is to say to simulate the renewable energy output. I mean, different wind farms, different solar farms, and then we simulate the whole year-round simulation. For example, the 8,760 hours per year. And then we simulate the power system under such output of renewable energy. That means we schedule the power system to see how power system would operate under different output of renewable energy. And then we get day-by-day operation of the power system, and then we evaluate how the power system operation acts. For example, the security and air pollution, the fuels it cost, and the money it cost. So we can evaluate the power system in various aspects, and we can compare different planning schemes, and then we can have a scientific comparison between different planning schemes. So this is the typical outcome of a power system operation simulation result. We can see this is example of power system in Inner Mongolia in China, about 2 weeks operation. Here, the black line denotes the load of electricity. And then the orange one denotes the operation of CHP generation. And the purple one denotes the thermal generation. And because this province is dominated by wind power, so there's a lot of wind power here. And the green line beyond this power load curve is the wind power that can be used for electricity heating. That means the space heating, because Inner Mongolia is really in the north and it needs the heating in the winter. And then the green one means the wind power that need to be curtailed in this time period. Then we can see because wind power is really have intermittency. That means in some days there's very windy days in a week, but in some time the wind is not that much. That means in some time the wind power has to be curtailed because the power system do not have enough flexibility. So the power system need more flexibility like storage to help to accommodate renewable energy. We have developed great optimal planning tool for power system. That is a self-developed power system planning, decision-making, and evaluation platform, which can simulate the power system operation day by day. And this is this platform has been applied in China's power system for a lot of provinces. And today I will take two examples for the application. One example is the interconnection between northwestern China and southwestern China. Because northwestern China has a lot of wind and solar, but southwestern China, including Tibet, has a lot of hydro. And this is the generation mix of the northwest China and southwest China. We can see that the northwest China has a lot of PV wind, and it has a lot of, but it has really small hydro. And so it has a lot of curtailment and lacks of flexibility. But in southwest China, there's a lot of hydro there, and it has a lot of flexibility, but it has a lot of seasonal imbalance. That means the hydro in the summer or autumn season has a lot of power that need to be curtailed. But in spring and in winter, the hydropower is not sufficient. It is insufficient. So what is the benefit of integrating northwest China and southwest China? So when it is interconnected, the generation mix is much more balanced. So we use this tool to calculate the benefit of interconnection. That means if we interconnect them, how much renewable energy curtailment can be reduced. And the result is very interesting, that the renewable energy curtailment would be largely reduced when interconnecting northwestern and southwestern China. The curtail rate will reduce from 8 to less than 1%. And also, this platform can calculate in detail how much capacity that we need to interconnect southwestern and northwestern. And the result is we need to have built the transmission lines with the capacity of 90 gigawatts. That has the optimal, has the most cost-efficient way of interconnecting northwestern and southwestern China, because beyond that, the benefit would be really marginal. The second example is that how to operate the power system, how is the typical and representative days in power system planning. And we use the power system operation simulation tool and to have a big data analysis. This is the procedure. I will not go into detail, but I will show you some interesting results. We operate a power system simulation for different penetration of renewable energy. That means 20%, 33%, and 40%. So this is the operating result. And then we take this to a big data analytic platform, and we analyze the different days in the power system, how it operates, and how close it looks to each other. And this is the result. This result shows that when integrating a really small amount of renewable energy, the operating days are really similar because the days are dominated by by the hydro and also by the typical load. But if we integrating more renewable energy, the days become dispersed. That means there's more diversity in different days. For example, in each season, we have 3 typical days instead of 1. If we integrate them more, for example, we integrate them in 40%, the days become more diverse. That means under high penetration renewable energy, we need a lot more typical days than the traditional one. So this is just 2 examples. The next, I will introduce generation, transmission, and storage load integrated planning. We also developed a platform to do the long-term planning of power system. So this is the typical power system interconnection in China. And in future power system, when we integrate more renewable energy, how the China power system look like? This is the question that we need to address. In a traditional planning approach, we use the power curve like this. This is the duration curve, but this curve ignores the time sequence of the power load. But when we have renewable energy integration, we need to take into consideration the time sequence of the power load. That means we need to incorporate the polynomial hourly operating simulation in power system planning. So this is really a hard work because this polynomial hourly operation simulation is really, really hard, and it involves a lot of variables. And how to integrate this operation into the power system planning model is really, really, really hard. We figure out some solutions for calculation. For example, from the spatial scale, we aggregate different generation units into clusters to reduce the variable. And from the temporal scale, we aggregate of different time series to make the calculation more efficient. And this is the overall model of generation, transmission, storage, load, co-planning formulation. And I will not go into detail about this model. I would like to share some results. The first is the China's power system planning towards carbon neutrality. Now, we have some conclusion. The energy penetration rate of renewables, such as, sorry for that. Sorry. So this figure shows that the generation mix of different provinces in China towards the 2050 targets. That means the carbon neutrality targets. And that renewable energy will reach 70% by 2050. That means more than 3,000 gigawatts of wind and 23 gigawatts of that means the 3,000 gigawatts of solar and 2,000 gigawatts of wind. And the coal power will be reduced by about 60%. And the gas power, biomass, and energy storage and CSP will provide a flexibility to the variable renewable energy. And we can also see from the result about the transmission lines that about 830 gigawatts of new interprovincial power channel will be built, both AC and also DC. AC and DC is half and half, and but the DC will be still stronger and more direct than AC, and this is the grid pattern of China in 2050, and we can also see the interprovincial exchange of China's power system. The power exchange will reach about 6,000 terawatt hour per year. That means it is 4 times of the current situation in 2020. That means though in 2050 we do not have load and renewable load and generation about 4 times, we are not reaching that far. It's only about 2 times, but the interconnection will be reached 4 times. That means when we deliver 1 megawatt of energy, it needs more energy transmission in the future. So, and also the energy flow in China will also keep the west to east power transmission and also the north to south power transmission. And so this is the basic idea of what I shared today, and I will draw some conclusions. The conclusion is that high penetration of renewable energy will put an increasing bundle of challenges. That means different technologies, various technologies is able to tackle these challenges, but the overall structure of the future power system will depend on the relative cost effectiveness of these technologies. And also the power system will be changed when the penetration of renewable energy is higher than 20% to 30%. And the year-round operation simulation is required for power system planning. And also the planning of the generation, transmission, storage, and load should be coordinated under high penetration of renewable energy. They cannot be doing one by one. They need to be coordinated. And the above requirement needs new modeling and computational approaches. And there's a lot of issues to be further addressed, which include efficient operation planning methods, market design, stability analysis, and also the new generation of accurate forecasting of renewable energy, and also the grid scale storage, such as power to hydrogen. So in power system, in the future, there's a lot of challenges, and in the planning stage, we have some preliminary work, and I would like to share this work to you. And if you have questions, please do not hesitate to contact me. Thank you very much.